All right, so day 2 for functions. We're identifying functions today. So let's explore the idea. Plot the ordered pairs for each table or from each table to represent the relationships as graphs. Then answer the problems. Number 2. The table below shows the number of dog licenses issued in the town of Palmer over a 5-year period. On the blank graph to the right, label and number the axes, then plot the ordered pairs. So we'll go ahead, since we know that our graph is going to go up to at least up to 150. We'll make sure we have at least that many on our y-axis. We'll just start it at 0 and then go up by 25. Oops, sorry. And 300, and we'll stop there. And then we'll just go by ones for our y-axis. Okay, and we'll go ahead and label our input. Our x-axis is always our input axis, so that's our years, and it's our input. And then we have our number of dog licenses. Which is our output. Okay, and we'll go ahead and plot. So we have 1 year is going to give us 75 dog licenses, 2 years 100, 3 years 125, 4 years also 125, and 5 years 150. All right, so we plotted, we've labeled. All right, number 3, describe the relationship between the input and output values. So what you could put here is that you could put that the input identifies a particular year, and the output it gives a number of dog licenses issued in that year. All right. And we'll go ahead and move on to number 4. Dogs age faster than humans do. Some people claim that dog years are a function of human years, as shown in the table. On the blank graph to the right, label and number the axes, then plot the ordered pairs. Again, we said that the x-axis is always going to be our input, so that means we're going to have our x values be the age in human years. We'll just say human years, and since that's going by ones, we'll just go ahead and label that. And then we have our age in dog years. We'll just call that dy. That's our y-axis, which is our output. And of course, our age in human years is our input. And they wanted us to go ahead and plot those order periods as well. I'm seeing this is going by sevens, so I'm just going to make mine go by sevens as well, because that's just what I'm seeing with my data. That was a 35. We'll stop at 70. All right, so 1 year in human years is 7 dog years. 2 is 14, 3 is 21, 4 is 28, and 5 is 37. All right. Then number 5 says describe the relationship between the input and output value. So what you could put here is that each output value is 7 times the input value. And you can prove that that's true because to get from 1 to 7, I multiply by 7. From 2 to 14, same thing. 3 to 21 times 7, same thing. So every time I want to get from an input to an output, I just know that my output is going to equal my input multiplied by 7. And we know our output is our y, our input is x times 7. So that would give us an equation here of 7x. Do you notice that with our equation that we wrote here, it doesn't have any plus or minus here? So that's interesting to say, but I just thought that was interesting to put. Okay, and that is it for this one. Let's go ahead and move on to the next page. All right, so let's talk about it. Answer the questions or problems below as a group. Let's go ahead and review these. Number 6, the relationships on the previous page are shown as graphs. Which graph or graphs show exactly one output for each input? Which set or sets of data represent a function? So in both graphs on the previous page, there is exactly one output for each input. So they are both functions. All right, and we'll go ahead and move on to number 7. Think about the function related to dog licenses. Would there ever be 1 year that is assigned to 2 different quantities? And explain. So the answer here is no. There is only one exact number of dog licenses issued in any year. It is not possible to have 2 different quantities. All right, and we move on to number 8. Look at your answers to problems 3 and 5 on the previous page. Can you represent either of the functions right with an equation? So the dog years function can be written or expressed as d equals the dog years. Sorry. The dog years function can be written as d equals 7h. But what I wrote on the other page was y equals 7x. D here is our output and h was our input. And of course, these are just variables, so of course you can swap them out should you choose to do so. Okay. And the dog function cannot be described, or the dog license one cannot be described with an equation though. Cannot be described with an equation. And if you look at the dog license one up here, the reason we say that is if it continued on in a line, like a straight line like here and here, and I'll use that in a different color. If it was like this and then this, then we'd have a predictable outcome. But we had two points that were 125, in the output, and you can't really predict that, and you can't really write an equation for that. So there was no way we could write an equation for the dog license, but it was still a function because each input had its own output. All right, and we will move on to number 9. Substitute values in the equations to complete the tables, then state whether each equation represents a function and explain your reasoning. So our equation is y equals x plus 2. So all you do is, since x is your input and y is your output, every time we have a new input, we just add 2 to it to get our output. So -2 plus 2 is 0. -2, or I'm sorry, -1 plus 2 is +1. 0 plus 2 is 2. 1 plus 2 is 3. And 2 plus 2 is 4. It says, and is this a function? Yes, it is a function. And we know it's a function because each output is 2 more than the corresponding input. So each input can only have one output. And I wrote that kind of big, so I'm going to move that up a little. And make it a little bit smaller. All right. And let's go ahead and move on to the next one. Y equals 4x. So all we're times 4 is 4, and 2 times 4 is 8. Is this a function? Yes, it is a function because each output value, oh, I spelled value super wrong, value is 4 times the corresponding input value. So each input can only have one output. Okay, and that is it for day